Okay, this is the start of Unit 15 here, and we're working on some material in Box 15A. We're going to look at the second derivative test, which, like the first derivative test, is a way of determining whether a critical number represents a local maximum or a local minimum. So let's just sort of recap what we know about local maxima and minima. We know that the local max and minima, local maxima and min, occur at what we called critical numbers. Okay, and we found our critical numbers by taking our derivative, okay, and setting it equal to 0. So a critical number is where the derivative at that number equals 0, or the derivative does not exist at a critical number if, let's say, x equals c is a critical number. Okay. So this was this whole thing about finding local max or local min. We take our derivative, set it equal to 0, and solve for x, and those x values are our critical numbers. And then we had to ask ourselves, how do we know if this point, x equals c, is a local max local min, local minimum, or neither? Because, of course, just because the first derivative is 0 at that point doesn't necessarily mean that there is a local maximum or a local minimum there. It could also be what we call a point of inflection. Or there's a few other weird things that can be happening with your curve that are going to make the derivative 0 or not exist. So how did we figure this out? Well, the method we've been using is the first derivative test. We checked the sign of the first derivative on either side of our critical number, and if it went from increasing, if our first derivative went from positive to negative, we knew we had a local maximum, and if it went from negative to positive, we knew we had a local minimum. So we were looking for a sign change in our first derivative. Another test we can use to do the same thing is what's called the second derivative test. So with the second derivative test, we know right away that we have found our critical numbers. So f primed at c equals 0. Okay. And what we're going to do is we're going to take the second derivative of our function, and we're going to check to see whether it's positive or negative. So if our second derivative evaluated at that critical number is greater than 0, okay, it's positive, then our function f has a local minimum at c. Okay. Now, how do you remember this? Well, second derivative greater than 0, so second derivative positive. Curve goes like that. It's a local minimum. If, on the other hand, our second derivative is less than 0, that means it's going to be negative. Negative, negative. That guy isn't very happy. We're going to have a local maximum at that point C. So if f double primed at c is less than 0, then f has a local max at c. Okay. And there's a third possibility. It could be possible that our second derivative is not positive, it's not negative, it is in fact exactly equal to 0. Okay? In this case, you can't use the second derivative test. It's not going to work. So we would say the test does not work. It doesn't mean there's anything wrong with your function or there's anything wrong with the critical point. It's just that this test doesn't work in all cases. So if you find that the second derivative equals to 0, second derivative test isn't giving you any information about whether you have a positive, a local maximum or a local minimum. So what you should do is go back and use the first derivative test. Okay. To work it out. Okay. So that's our second derivative test. Okay. So let's try applying this to an example here. Okay. And here's the kind of question we've been working on before. Determine the local maximum and minimum of some function here. Okay. So we can start this the same way we've worked at this all along. We're going to take our derivative, okay, and set it equal to 0. So our derivative here is going to be 15x to the power 4 minus 75x squared plus 60. And we're going to look for our critical numbers. Our critical numbers occur where f primed at x equals 0 and f primed at x does not exist. Okay. Now we haven't talked very much about the cases where the derivative doesn't exist. And that's because mainly we've been working with polynomial functions up until now. We're starting to move into working with rational functions using the quotient rule and things like that. So we're going to come across cases, I think, where the derivative does not exist, and we're going to have to look at how you handle those cases, especially in Unit 16 when we're sketching graphs. But for this function that we've got right here, it's a nice polynomial function, so we just have to look at cases where our derivative is equal to 0. So we set this thing equal to 0, and we start to solve. Let's see, how can we solve this? Well, we can divide through by the 15 to get x to the power 4 minus 5x squared plus 4 equals 0. And then we can factor this. We're going to have x squared, 4, 1, and they're both going to be negative. So x squared minus 1 times x squared minus 4. And then from here, we can factor it once more, because these are both differences of squares. X minus 1, x plus 1, x minus 2, x plus 2. So our critical numbers are, and I'm not sure why I wrote a 4 in there, plus 1, my mistake. So our critical numbers here are x equals positive 1, negative 1, positive 2, and negative 2. So 4 critical numbers. If we were applying the first derivative test, we would have, I guess, 5 columns on our chart that we'd have to fill in. But let's use the second derivative test. So we'll go back to our function here, well, in fact, the derivative of our function, and we will take the second derivative here. So we've got 4 times 15 is going to give us 60x cubed minus 150x, and that's all we need. And what we want to do is we want to evaluate f double primed at each of those critical numbers. So we'll evaluate it at +1, -1, +2, and -2. Okay. So this is basically just calculator work here. So let's just write down what the answers are. We get -90, +90 at -1. We get 180 at x equals +2 and minus 180 at x equals -2. And then we're just going to use this to figure out whether these are local max or local min. So if we look at where x is +1, let's see. Our second derivative here is negative. So this is local maximum or local minimum. Well, this is going to be a local max. Where this thing is positive, well, let's see, positive, positive, we're going to have a local min. Okay. And same thing for these next two here. If our second derivative is positive, we are going to have a local minimum. And if it's negative, we are going to have a local max. And so in addition to doing this, you'd go back and you would figure out what the coordinates are for all of these points. So this one here is, let's see, we got a local maximum at 138, a local minimum at -38. Okay. And for x is +2 and x is -2, we've got, let's see, this is 216, and this is at -2, this is -2, -16. Where did I lose that? Right here. Okay. Okay. So just subbing those numbers into the formula lets you know whether you've got local max or local min. Okay. And we can always confirm this just by taking a look at what our function would actually look at. Got a graph of it sitting right here. Notice this is just going sort of up and down as we go along. So we've got local max, local min, local max, local min. Okay. And that's the second derivative test.